This video is going to have a look at metallic bonding, and we've had a look at covalent and ionic and two different types of covalent in terms of simple and giant covalent structures. And we're going to have a look at the third kind of bonding, which is metallic. Now, this is a bit misleading because it's not actually a kind of bonding. Metals are a mixture. They're not actually chemically bonded to each other. So we don't refer to them as an actual, we wouldn't refer to them as a compound. We would refer to them as a mixture. Now, let's try and take an example here. So I tend to use lithium. Now, lithium starts off with one electron on the outside. That electron, let's say, wants to move, because metals always lose electrons, wants to move over here. However, this lithium here has already got one electron, and it's not strong enough to hold on to two. So its one electron that was blue decides, actually, no, I'm going to go over here, which means that this one here, this green electron that was on this lithium here, is no longer able to be held on, so that one moves over onto this lithium, and so the pattern just continues, constantly having electrons move from one atom to another. So the electrons have never actually got a set position. They are what we call delocalized, which means that when we actually represent these, because they're sort of bouncing from one shell to another, from one atom to another, what we do instead is we represent those metal ions, or the metal particles, as cations, positive ions. And that's the positive charge that's left over when they lose the electron, the outermost electrons. Those electrons are then just drawn without any particular location. They're what we call delocalized. So we've got some delocalized electrons around the outside, and as a result, the definition of a metallic bond is a regular lattice of positive cations surrounded by a sea of delocalized electrons. Now, this is a diagram for how that might be demonstrated. One of the key factors here is that because these form regular lattices, and this is, bear in mind, only when it's an actual metal, an element, it means that we can move the rows of positive cations, and that makes them quite malleable and ductile. It also means that all metals can conduct electricity because those electrons haven't got a home, they're delocalized, they can flow through. If we want to turn this into an alloy, what we'd do is we'd put a bigger, and we'll do another video on that, but we'd put a different metal in, which would give us a bigger cation or a smaller cation, which would disrupt this regular arrangement, which would make it a lot stronger. And that's pretty much all you really need to know about metallic bonding. And the key phrase here is a regular lattice of positive cations surrounded by a sea of delocalized electrons.